How's it going, everyone? I'm back with another video, and today is going to be all about stoichiometry. Stoichiometry is just a fancy way of saying that we're going to be looking at the proportions between reactants and products in a chemical reaction or chemical equation. So if I start with a certain amount of reactant, I should be able to figure out how much product it's going to create for me. Now, the second part of this video is about limiting reactants, and that'll go more into what limits a reaction in terms of how much product we can create. But before we get into that, we do need to make sure that we know some core skills. And the first one is balancing chemical equations. And if you need more practice on this, feel free to watch my video on balancing chemical equations, and then you can come back to this video. The second thing you need to know is the mole triangle, which is what I have written over here. And the mole triangle is going to help us solve for number of moles, mass, or molar mass, depending on the situation. And I'll just go through a quick example of how we would do that. Based on the way that our variables are written in the triangle, it tells us how to solve for it. So let's imagine I want to solve for the number of moles of oxygen that I have, and I have a mass of oxygen of 20 grams, and I know that the molar mass of oxygen is 15.99 grams per mole. So, based on the triangle, if I want n, I'm left with little m on top and big M on the bottom. Little m refers to mass, and since it's on top of big M, which is molar mass, I need to divide the two, dividing mass by molar mass, and I get a value of roughly 1.25 moles. And just a reminder that 1 mole is roughly 6.02 times 10 to the 23 units. So the reason why we count things in moles is because atoms and compounds are in such high abundance that it's much easier to count them in moles. And sometimes students forget what each variable represents in the mole triangle. So I'll just write that out quickly here. So we have mole, mass, and molar mass. Last thing we need to look at is mole ratios. But in order for us to understand mole ratios, we first need a balanced chemical equation. So let's look at this example down here and quickly balance it. On my left-hand side, or reactant side, I have hydrogen and oxygen. And I guess we could say that these are in gas form. And on my right-hand side, we have water. On my right-hand side, I do have 2 atoms of hydrogen, which is the same on the left. So that's already balanced. But in terms of oxygen, I have 2 on the left and only 1 on the right. So I am going to have to balance that out with a coefficient of 2 on water. But what that does is it introduces more hydrogen, because now I have 4 hydrogen atoms on my right-hand side. So I need to add a 2 to this side to make everything balanced. Okay, now that we have a balanced equation, we can look at mole ratios. Mole ratios refer to the coefficients in front of each of our compounds or elements. And whenever something is blank like this, we can just imagine that there's a 1 in front. What's special about a balanced chemical equation is that the coefficients in front of our elements or compounds actually give us the mole ratios in terms of how much reactant is reacting to form a certain amount of product. We can see here that I have a 2-to-1 mole ratio between hydrogen and oxygen, meaning that for every 2 moles of hydrogen that react, 1 mole of oxygen is reacting. And when that happens, we create 2 moles of water. So we can either compare the coefficients between reactants, or we could also look from one reactant to a product. So if I look at oxygen compared to water, I could say that there's a 1 to 2 mole ratio, because for every 1 mole of oxygen that reacts, I get 2 moles of water. All right, let's see if we can put all of these skills together in our first full stoichiometry question. So in this example, we have copper chloride reacting with aluminum metal to give us aluminum chloride and copper metal. And the main question is, how much copper will be produced if you start with 110 grams of aluminum? So I'm just going to write that we have 110 grams of aluminum here. But before we can really start with this question, we do need to make sure that our equation is balanced to get accurate mole ratios. And let's do just that. I can tell that chlorine is not balanced because I have 2 atoms of chlorine here, but 3 atoms of chlorine here. And if I want to make them have the same amount on my reactant and product side, I would need to put a 3 on copper chloride and a 2 on aluminum chloride. However, when I do that, I've introduced a lot more metal into the equation. So I would need to put a 2 on aluminum to balance the amount that I have here, and I would need to put a 3 on copper to balance the amount that I have here. Okay, that looks good. The next step is to think about mole ratios, because if we look at the mole ratios between aluminum and copper, we can see that there's a 2 to 3 mole ratio. So that means for every 2 moles of aluminum that react, I'm going to get 3 moles of copper in my product side. In order to make use of mole ratios, we do need to work in moles. So I do need to convert this mass of aluminum into moles. We know that number of moles can be calculated by dividing mass by molar mass. And we have mass. Molar mass can easily be found from the periodic table. And the molar mass of aluminum is roughly 26.982 grams per mole. Let's divide our values. And we have a roughly 4.077 moles of aluminum. Now we can take this number and apply it onto our mole ratio. And we're going to do that with a little bit of multiplication, because I have this amount of aluminum, and I'm going to be getting 3 moles for every 2 moles of aluminum. I could write that as a fraction. And multiply it by the number of moles I have, because this is aluminum. If I multiply it by 3 over 2, I'll be removing the value for aluminum and instead finding the value for copper. And 4.077 times 3 over 2 is roughly 6.116 moles. So this is in fact how much copper would be created in this particular situation. However, most questions are actually going to ask you for this answer in mass or in grams. So we need to solve for little m. And when we do that, we take the number of moles and we multiply it by our molar mass. So let's do that. 6.116 times the molar mass of copper, which is a bit higher than aluminum. I believe it is 63.55 grams per mole. And once again, if you're not given molar mass in a question, you are going to have to find it from the periodic table. So down here, we are solving for mass. We get about 388.67 grams of copper. And if your teacher is being super specific, they might ask for your answer in appropriate significant figures. In our question, we were given this number, 110 grams, which has two significant figures. So our answer needs to reflect that. We could say roughly 390 grams of copper was formed. Okay. That is the general way to solve for a stoichiometry question. But we do have to consider what I alluded to earlier, which is the idea of a limiting reactant. Because this is going to be a much more realistic situation where I have two varying amounts of reactant, because a lot of reactions have more than one reactant. And the amount of product that I create is going to be dependent on only one of those reactants. So we need to figure out which one of those is going to be 100% used up and which will leave an excess amount that won't react. And my favorite way to explain this is to think about baking a cake in terms of the amount and ratio of ingredients that we need to create a cake. Let's imagine I have a recipe, and in this recipe, I need 1 cup of flour and 3 eggs to create 1 slice of cake. And that's going to be a very thick slice of cake because 1 cup of flour is a lot, but that's okay. If I were to start with 5 cups of flour and 18 eggs, the question is, how many slices of cake can I create? Well, I have this ratio for my ingredients up here, and we can actually think of that as like a mole ratio, where I have a 1-to-3 ratio in terms of cups of flour and eggs. So if I wanted to completely use up 5 cups of flour, I would need 3 times as many eggs. So I would need 15 eggs to use up all of my flour. But if I have 18 eggs and I want to use up all of my eggs, I would need 1/3 the amount in cups of flour. So I would actually need 6 cups of flour. And if you want to show that mathematically, you can just using the mole ratio, where if I take 5 cups of flour, I could times it by our mole ratio, just like we did in the last question, and that gives me the amount of the other reactant that I need. But anyways, back to our values. I can see that I have enough eggs to use up all of my flour, because I have 18 and I only need 15. But if I wanted to use up all of my eggs, 18 eggs, I would need 6 cups of flour. And this means that flour is our limiting reactant. Right? Because the amount of cake I can create is totally dependent on how much flour I have, because it limits the amount that I can create. The amount of eggs that I have, I could say, is in excess. So this is my excess reactant. The amount of cake I create is not dependent on how many eggs I have, but in terms of how many cups of flour I have. All right, hopefully that made some sense. And to check our understanding, let's try a more scientific question. So for this one, we have lithium nitride and water reacting with lithium hydroxide and ammonia. And the question is, for the following reaction, how many grams of lithium hydroxide will be formed? So very similar to our first stoichiometry question. However, this time we have 2 reactants with 2 amounts or 2 different masses. And one of them is going to be our limiting reactant. So one of them will determine how much lithium hydroxide will form. But the first step is still the same. We need to balance our chemical equation and also think about mole ratios. So let's do that. Now, usually with chemical equations, I start by balancing oxygen and hydrogen, but I can tell immediately that we have 3 lithium atoms on the left and only 1 on the right. So I'm going to add a 3 here. And now I've introduced more oxygen on my product side. So I have 3 atoms of oxygen here, and I would need to add a 3 here to balance that out. Looking at my hydrogen, it looks balanced because I would have a total of 6 atoms of hydrogen here, and then 3 from lithium hydroxide and 3 from ammonia on my right-hand side. So that looks good. And finally, we've only got 1 nitrogen on both sides. So this equation is now balanced. Second thing we need to do is we need to convert our masses into moles, and let's do just that. So we're looking at a lithium nitride. I have 12.5 grams. I need to divide not by the molar mass of an individual element, but by the molar mass of the entire compound. And the way I'm going to do that is I'm going to take the individual molar masses of my elements in the compound. So the molar mass of a lithium is 6.9410, and the molar mass of nitrogen is 14.007. Now, I have 3 atoms of lithium in every lithium nitride molecule, so I would actually need to multiply the molar mass of lithium by 3. And I would add the molar mass of nitrogen, just 1 instance of it, because we only have 1 atom of nitrogen in our molecule. And when we plug all of this together, we get roughly 0.3589 moles. Okay, let's do the same thing for water. Molar mass of oxygen, we already know from our previous example. And the molar mass of hydrogen is very close to just 1. Once again, we need to think about how many atoms of each element we have in a molecule of water. I have 2 atoms of hydrogen, so I'm going to multiply the molar mass of hydrogen by 2, and I'll add that to, this should be a 15.99 to represent oxygen. Here we get 0.9164 moles. We have everything in moles, but which one of these 2 reactants is our limiting reactant? And that's going to determine how much lithium hydroxide we can create. Lithium nitride and water have a 1:3 mole ratio in this scenario. So for every 1 mole of lithium nitride, I need 3 moles of water. And let's see if I have that ratio for lithium nitride. If I take 0.3589 and I times it by our ratio, I get 1.08 moles. And I can tell that this is much larger than 0.91. So I don't have enough water to react to all of the lithium nitride that I have. However, I need 3 times as much water as I do lithium nitride. So if I work backwards, starting from my amount of water that I have, if I divide this value by 3, I'm going to see how much lithium nitride I need to get rid of all of my water. And turns out I only need 0.3 moles of lithium nitride. What this means is water is my limiting reactant because I only need 0.3 moles of lithium nitride to use up all of the water that I start with. And when that's done, I'm going to have an excess amount of lithium nitride. And we're going to solve for that amount in part 2. But first, let's figure out how much lithium hydroxide is going to be formed here. Now what I want to do is I want to compare the mole coefficients of water to lithium hydroxide. And I can see that we have a 3-to-3 mole ratio, which really we can think of that as a 1-to-1 mole ratio if we reduce it. So if I have 0.9164 moles of water, I'm going to end up with 0.9164 moles of lithium hydroxide. It's that simple. Now all we need to do is convert this amount of moles into mass. Once again, mass will be moles times molar mass. And in this case, we have moles. We just need to figure out what the molar mass of lithium hydroxide is. Luckily, we already have all of the molar masses of the individual elements. So lithium is this, oxygen is this, and hydrogen is this. And when we plug all of this into our calculator, we are going to get 21.9 grams of lithium hydroxide. And again, I just put my answer as 21.9 grams because I would have 3 significant digits here, and the values that the question gave us also have 3 significant digits. Okay, we are almost done. We just need to figure out how much lithium nitride will remain. We know that we used up 0.305 moles of lithium nitride. So if I figure out the mass of this number of moles and subtract it from our initial amount, that's going to be how much is left over. So let's do just that. So we want mass, we already have moles, and we're just going to reuse the same molar mass that we used in the first part of this question. And plugging all of this in, I get 10.6 grams. So if I subtract that amount from my initial amount, I am left with 1.9 grams of lithium nitride. And this is our answer. All right, that was an example for a general stoichiometry question and also a question involving a limiting reactant. Hopefully you found both of those examples useful. Thank you so much for watching, and good luck studying.